So now let us concentrate on the characteristic feature of the wave function. So this is the expression for the normalized wave function one gets on solving Schrodinger wave equation for particle trapped in a one-dimensional box of length a. Okay, where n represents the quantum number which cannot be 0. N is equal to 1, 2, 3, etc. And x represents the position of the particle inside the box. Now you can clearly see from this expression that when you solve the Schrodinger wave equation, we do not end up with one function, one wave function, but we end up with an infinite set of wave function. I repeat, when a Schrodinger wave equation is solved, okay, one ends up with infinite number of possible wave functions, that is eigen function. Why? Because if I substitute different values of n from varying from 1 to 3 up to infinity, because theoretically the value of n can be varied from 1 to 3 up to infinity. So by substituting different values of n, we can get different expressions for wave function, that is eigen function. So theoretically speaking, there are infinite number of eigen function. So that is why I told, when a Schrodinger wave equation is solved, we get an infinite set of wave functions, that is eigen function. And remember, these wave functions or the eigen function represents the state of the system. Okay, I repeat, these wave functions or the eigen functions represent the state of the system. Okay, what is the exact meaning of this? I'll discuss this again when we talk about postulates of quantum mechanics. Now I will not go into those details in more details now. Okay, so if suppose n is equal to 1, how will you write psi 1 of x? So psi 1 of x is equal to square root of 2 by a into sine n pi by a into x. So this represents the wave function corresponding to n is equal to 1, and n is equal to 1 represents the lowest energy or the ground state of the system. So this is the ground state wave function. This wave function represents the ground state of the system, and it has energy E1 is equal to h square divided by 8ma square. So this wave function, which represents the state of the system, it has the corresponding eigenvalue of energy E1 h square by 8ma square. What do you mean by psi 2 of x? It means I have to substitute now n is equal to 2. The next possible n is equal to 2. So that would give square root of 2 by a into sine. Sorry, here n is 1. Okay. So this is 1 into pi. So simply pi by a into x. So here n is equal to 2. So it becomes 2 pi by a into x. And this corresponds to the state of the system where n is equal to 2, which is the first excited state of the system, and it corresponds to an energy E2 is equal to 4h square divided by 8ma square. This is the eigenvalue of energy corresponding to this eigen function, which are obtained when the Schrodinger wave equation is solved. Similarly, you can write psi 3 of x corresponding to n is equal to 3, which is square root of 2 by a into sine 3 pi by a into x, corresponding to eigenvalue of energy nh square divided by 8ma square. So this wave function represents a state corresponding to n is equal to 3 and having energy E3. This represents the second excited state, n is equal to 3. So similarly, you can write the expressions for n is equal to 4, 5 and so on. So the psi 1 of x is different from psi 2 of x, it is different from psi 3 of x, as they represent different states corresponding to n is equal to 1, 2, 3, and they correspond to different energy. Okay, and we exactly do not know whether the particle is in the state corresponding to psi 1, whether it is in the state corresponding to psi 2, or whether it is in the state corresponding to psi 3. What do I mean? I will explain. Okay, so let me draw the energy level again. Okay, so this is the one-dimensional box. Okay, x is equal to 0, x is equal to a, and this represents the energy. Okay, starting from 0, but in this case the particle will never have zero energy. So the lowest non-zero energy it has corresponds to n is equal to 1. So this corresponds to n is equal to 1, and the energy of the particle is E1, and it corresponds to the wave function psi1 of x given by this equation. The next state is n is equal to 2, corresponding to energy E2, and corresponding to the wave function psi2 of x. So psi2 of x corresponds to the state where the particle is present in the second level. Okay. Similarly, the next possible level is n is equal to 3, corresponding to energy E3, and described by the wave function psi3 of x. And the next possible energy is corresponding to n is equal to 4. The energy is P4, and this state is described by the function represented by psi4 of x. So if the particle is in a state corresponding to psi1 of x, what does it mean? It means that the particle is having energy E1 and it is in the state corresponding to n is equal to 1. Suppose the state of the system is described by the function psi4 of x. What does it mean? It means that the particle is having now energy E4 and it is in the excited level corresponding to n is equal to 4. So this psi1x, psi2 of x, psi3 of x, etc. they describe the state of the system. It means state of the system corresponding to a specific energy. For example, if I say the wave function is psi4 of x, it means the particle is having energy E4 and it is in the state corresponding to n is equal to 4. So when we solve a Schrodinger wave equation, we do not get one solution, we get infinite set of solution. Now suppose if the temperature is very low, okay, T is very low. So if the temperature is very low, then in such cases we can assume that the particle in most of the case is in its ground state. So because the temperature is very low, the energy of the particle will also be very less. So we can assume that in most of the cases the particle is expected to be in the lowest state. So in such cases the state of the system is best described by the wave function psi1 of x, because we can tell with the certainty that surely that the particle is in the ground state because the temperature is very low. If I increase the temperature, if the temperature is very high, then there is possibility that the particle may be present in n is equal to 1, or it might have absorbed energy because we are heating, we are increasing the temperature, it means we are heating, the particle may absorb energy and it may be in any excited state. It may be in n is equal to 1, the ground state, or it may be n is equal to 3, 4, 5, any state. So in such cases we exactly do not know to which wave functions the state corresponds to. Okay, so which wave function should I use, psi1 of x, psi2 of x, psi3 of x, because we exactly do not know in which particular state the particle is. So what we do is, in general, the wave function psi of x is written as a linear combination of all these functions. So I simply write it as a1 into psi1 of x plus a2 into psi2 of x plus a3 into psi3 of x, and so on, a n of psi n of x, so on. Okay, where this subscript 1 represents the value of n. So here n is equal to 1, here n is equal to 2. In general, you can have infinite number of terms. So this wave function represents the actual state of the system, because we do not know whether the system is actually in a state corresponding to psi1, whether it is in a state corresponding to psi2, or whether it is in a state corresponding to psi3. So in general, we simply write psi of x as a linear combination. This can be written as summation of an into psi n of x, where n varies from 1 theoretically up to infinity. Okay, so this is the linear combination of all the possible wave function. Okay, generally we express this is the solution for a Schrodinger wave equation, but we will not make that thing that complicated. If the temperature is very low, what will happen? Okay, if the temperature is very low, then the system will be in its ground state, and that ground state will be represented by the wave function psi1 of x. So the coefficients a1, a2, a3, a4, etc., they play a very important role. What is their role is the value of a1, a2, a3. Okay, what I'm saying is not the exact quantitative uh, statement. Okay, I'm making a rough statement. Okay, so the values of a1, a2, a3, etc., which are the coefficients associated with each wave functions, so their value decides which wave function gives the highest contribution. Suppose if the value of a1 is much greater compared to a2, a3, an, what does it mean? This overall wave function, okay, has the highest contribution from the wave function psi1 of x. If a2 is much greater compared to a1, a3, an, etc., then the overall wave function psi of x is in this best possible way, it is represented by the wave function psi2 of x. So when the particle is in the ground state, we can assume when the temperature is very low, we can assume that the particle is in the ground state. So the state of the system is better represented by wave function psi1 of x. What does it mean? It means that a1 becomes equal to 1 in that case, and all a2, a3, a4 up to an all become 0. So in such case, psi of x is nothing but a1 is 1 into psi1 of x. So the ground state, this is nothing but the ground state. So at the very low temperature, okay, at very low temperature, the higher energy states contributions are very less. Okay, so you can talk about this in much detail, and things get complicated. We will not discuss that much here. If you come to the MSc course of quantum chemistry, then we have to discuss these things in much elaborated way. So what I wanted to say this is, when you solve the Schrodinger wave equation, you get a infinite set of wave function which represents the different state of the system, and that wave function contributes the highest, that wave function contributes to the highest to the wave function, okay, corresponding to which state the particle is. For example, if the particle is in the ground state, okay, especially at low temperature, it means the wave function psi1 of x makes maximum contribution to the overall wave function. Okay, let me not discuss this in much detail. What we are now interested is, let us plot this graph, okay, in a potential energy diagram, or in the potential energy, sorry, not potential energy, in the particle in a box diagram. Let us try to plot this psi1 of x, psi2 of x, psi3 of x, so on, and let us see some important features. Okay, so on one side, okay, again let me draw a graph of psi of x versus x. So along x-axis we are taking the position of the particle, which can vary from x is equal to 0 to x is equal to a, and y-axis we are plotting the wave function for different values of n. So n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on. Okay, so strictly speaking, this spacing that I have written is not correct. Okay, but here I am not interested in the energy, I am only interested in the wave function. Okay, so please ignore the inconsistency in this spacing. So for different values of n, I have already obtained the different wave functions. Now that I have to plot in the form of a graph. What I will do is, simultaneously I will also plot, okay, on the other hand, a graph of psi square of x. Okay, I will plot a graph of psi square of x versus x. So along x-axis, position, which can vary from x is equal to 0 to x is equal to a, and along y-axis I am plotting now psi square. Why psi square is important is, Okay, this is more important than psi. I already told you psi of x has the physical meaning that it represents the amplitude of the wave associated with the particle, but psi square of x has a greater meaning, physical meaning and importance. It represents the probability of finding the particle inside the box. So let me plot both the graphs simultaneously. Okay, corresponding to n is equal to 1, corresponding to n is equal to 2, corresponding to n is equal to 3, corresponding to n is equal to 4. Okay, now all these functions contain sine term, and you know how the graph of a sine function looks. The graph of a sine function is sinusoidal, that is a wave type graph. Okay, so when you plot wave function psi versus x, because you have sine theta terms in each expression, what we may expect is the pattern to be a wave like pattern. Okay, so for let us plot for n is equal to 1, that is we are plotting this graph by substituting different values of x from x is equal to 0 to x is equal to a. Let me try to plot. If x is 0, this term becomes 0, so psi 1 of x becomes 0. So when x is equal to 0, wave function becomes 0. This is true because of the boundary condition. Remember, I told you the boundary condition in the last class. When x is equal to 0, psi of x should become 0, and this becomes 0. Similarly, when x is equal to a, if I substitute x is equal to a gets cancelled, so you get sine pi, which is again 0. So psi of x becomes 0 when x is equal to a. So these two are nothing but the boundary conditions. So at these 2 points, the value of the wave function is 0. If I substitute x is equal to a divided by 2, x is equal to a divided by 2. What is a by 2? A by 2 is nothing but the center. Okay, this is nothing but x is equal to a by 2, that is this exact center of the box. Okay, so here also I will do the same thing. I am dividing the box into two vertical components. Okay, x is equal to a by 2. So if I substitute x is equal to a by 2, okay, a by 2, what happens? A gets cancelled, so you get sine pi by 2. Sine pi by 2 is 1. Okay, and you know that the maximum value a sine theta function can have is 1. So when I substitute x is equal to a by 2, this becomes pi by 2. So sine function takes its maximum value of 1. Therefore psi of x has the maximum value when x is equal to a by 2. So how this graph will look like is something like this. A half wave. A half wave, okay, which is symmetric in nature. It is symmetric with respect to the center of the box. Why? Because one half of this wave is a mirror image of the other half of the wave. So, and I call this as the positive phase of the wave. ಯಾಕಂದ್ರೆ ನೀವು ಯಾವುದೇ ವೇವ್ ತಗೊಂಡ್ರೆ ಒಮ್ಮೆ ಕ್ರಸ್ಟ್ ಬರ್ತದೆ ಮತ್ತೊಮ್ಮೆ ಟ್ರಫ್ ಬರ್ತದೆ. ಸೊ ದಿ ಅಪ್ಪರ್ ಕಾಂಪೊನೆಂಟ್ ಆಫ್ ದಿ ವೇವ್ ಲೆಟ್ ಅಸ್ ಟೇಕ್ ಇಟ್ as positive, the lower component of the wave is taken as negative. So at these two boundary conditions, x is equal to 0 and x is equal to a, wave function is 0 and it has maximum value at the center of the box. Now for n is equal to 2, again at the boundaries the value of the function is 0. Now instead of getting one wave, we get two waves. So instead of getting a half wave, we get one full wave, and the wave is something like this. So this is the plus phase of the wave, this is the negative phase of the wave, and you can clearly see that one half of this is not the mirror image of the other half. So this plot is not symmetric at the center of the box, and it contains how many half waves? Two half waves or one full wave. ಅದೇ ರೀತಿ n is equal to 3 plot ಮಾಡಿದರೆ you can predict n is equal to 1, there was one half wave, n is equal to 2, two half waves, n is equal to 3, there should be three half waves. So the three half waves will be something like this. So this is positive, this is negative, this is positive. Now again with respect to the center of the box, you can see that one half is the mirror image of the other half. So again this plot is symmetric in nature. Similarly n is equal to 4, okay, you get 4 half waves or 2 full waves. Okay, so you get two full waves. This is both, okay, are positive phase, These two are the negative phase. Okay, so again the one half of the pattern is not the mirror image of the other half, so this is also not symmetric. So n is equal to 1, n is equal to 3, n is equal to 5. So for odd values of n, the wave function psi of x are symmetric with respect to the center of the box, but for even values of n, n is equal to 2, n is equal to 4, n is equal to 6, and so on, the functions are not symmetric, the plots are not symmetric, they are non-symmetric. Okay, and an important observation that we have to make here is, for a given value of n, the wave function psi of x depends on the position of the particle. So as the position of the particle changes, the value of the wave function also changes. So if I take this point here, its wave function is given by this value. If I take a point somewhere here, its wave function is given by this value. Okay, so you clearly see that if the particle is at this particular position, it corresponds to wave function here. If the particle is at this position, it corresponds to a wave function here. So as you change the position, the wave function also changes. That is one important observation. But what happens in energy? As you change the position of the particle, the energy of the particle does not change. But here the wave function changes as the position of the particle changes. The second important observation we have to make is, other than these two boundaries, remember at these two boundaries, x is equal to 0 and x is equal to a, there are boundary conditions irrespective of n is equal to 1, 2, 3, 4, irrespective of the values of n, there are boundary conditions at x is equal to 0 and x is equal to a. So the value of wave function is always 0 at these 2 points. But there are other points other than these two boundaries, such as here at x is equal to a by 2, this is the center of the box. Okay, so other than these two boundaries, there is one more point where the value of wave function is 0. This point is called as a nodal point or a node. So what do you mean by a node? Node is a point in space other than the boundary points where the value of wave function becomes 0. So for n is equal to 1, how many nodes are present? 0 nodes. Okay, for n is equal to 2, there is 1 node, which is nothing but 2 minus 1 node. Okay, for n is equal to 3, there are 2 nodes. Okay, so there are 2 nodes, which can be written as 3 minus 1. 3 minus 1, that is 2 nodes. For n is equal to 4, there are 1, 2, 3 other than the boundaries. So there are 3 nodes, which can be written as 4 minus 1. So in general, if the system is in the nth state, there are n minus 1 nodes in the wave function. Okay, so if n is equal to 2, there is 2 minus 1, 1 node. If n is equal to 4, n minus 1, that is equal to 4 minus 1, there are 3 nodes. So remember, in general there are n minus 1 nodes in the wave function corresponding to a value of n. Okay, but this is of that much of is not of that much physical importance. Okay, what is important is the plot of psi square of x. So the plot of psi square of x is very easy. We have to just take the square of this. Okay, so when I take the square of this, the magnitude of this function changes a bit, that is a relative value. Okay, that we are not interested. The other change that happens is, if we have a positive component, if I take the square, it still remains positive. But if I take the square of this negative phase, okay, it also becomes now positive. So when I take this square, we have only the positive phase of the waves. Okay, so let us try to plot psi square versus x. So the psi square versus x for n is equal to 1, something like this. Okay, it should be drawn more properly. Okay, it should be symmetric. So I am struggling to draw here. So it is a symmetric graph. Okay, with the maximum value at the center, because here you have maximum value at the center of the box. So psi square also has a maximum value at the center. Similarly, when for n is equal to 2, if I take the square, okay, this graph becomes something like this. Okay, so you have only the positive faces. Okay, remember here it is still 0 because you have a node here, so here the value is 0. So if I take the square of this function, the graph will be something like this. Okay, all are positive. Similarly, okay, this is the graph. Okay, you have to uh, pardon me for uh, the diagram that I have drawn. Okay, that is these diagrams are drawn in a non-professional way. Okay, so if you clearly look and compare it with the psi versus x function, you can observe some similarities and differences. Okay, so here you have nodes again. Okay, that is obvious because here if you have nodes, you should have the corresponding nodes here also. Okay, you have corresponding nodes here. Now here you had both positive as well as negative component of the waves. Here you have only positive. And again you can see that the value of psi square varies with respect to position. For example, here when n is equal to 1, psi square is maximum here, whereas psi square becomes 0 here. Here psi square is maximum at this point and this point, here it is 0. Psi square is maximum in these 3 points, whereas it is 0 here. So the value of psi square x varies with respect to the position. Okay, and how many nodes are present? Same, n minus 1 number of nodes. If we comment on the symmetry of these plots, you can see that all the plots are symmetric in nature. If I take n is equal to 1, it is symmetric. One half is the mirror image of the other half. This is also the same. One half of the plot is the mirror image of the other. So for all values of n, whether n is odd or even integer, all the plots are symmetric in nature, whereas here the plots were symmetric only for odd values of n. But what more interesting is, what does psi square represent? Psi square represents the probability of finding the particle, and from our classical point of view, okay, we should expect the probability of finding the particle to be same at all the position. Okay, because the nature will not will not make any partiality towards a particular position. The probability of finding the particle at this point should be same as the probability of finding the particle here. It should be same as the probability of finding the particle here. It should be same as the probability of finding the particle here. So from our common sense, the probability of finding the particle should be same. For example, if I toss a coin, okay, the probability that I will get a head and the probability that I will get tail are one and the same. Okay, other if I am rolling a dice, okay, you should get 1 2 3 4 5 6. There are 6 results. So what is the probability that I will get 1, or what is the probability that I will get 2, or what is the probability that I will get 6? All the probabilities are same because nature does not make prefer any one event. It has no partiality. It does not make any partiality towards any particular event. So according to the nature rule, what we assume is all the events are equally possible. So the probability should have been same. The probability value should have been uniform throughout the box, irrespective of the position. Probability value should have been same, but it does not happen here. What does quantum mechanics predict? The quantum mechanics predict that in the ground state, the maximum probability of finding the particle is at the center of the box. So when the particle is in the ground state, it spends maximum of its time at the center of the box. Ade classical mechanics togondre, the probability of finding the particle should be the same at all the positions, which is not true here according to quantum mechanics. The things becomes more interesting if you go to n is equal to 2 state. What does this n is equal to 2 state tell is, again the probability is a function of position. As you change the position, probability values also changes, and the probability becomes maximum at these 2 points. This point corresponds to x is equal to a by 4, that is 1/4 of the length of the box, and this point corresponds to x is equal to 3a by 4, okay, that is 3/4 of the length of the box. Okay, so here the probability is maximum, here also it is maximum, but here we are seeing a point which is the center of the box where the probability of finding the particle is 0. How can this happen? You have 2 points, okay? You have 2 points, 1 point here, 1 point here, where the probability of finding the particle is maximum. But exactly at the center, you have 1 point where the probability of finding the particle is 0. It means the particle either spends most of its time at x is equal to a by 4 or at x is equal to 3a by 4, and it never spends even a fraction of the second at x is equal to a by 2, where because the probability is 0. How this is physically possible? Because if the particle has to spend maximum time at either x is equal to a by 4 or at x is equal to 3a by 4, if it wants to change its position, for example, particle x is equal to a by 4 okay, it spends some time there, then it wants to move to x is equal to 3a by 4. Why? Because there also the probability is maximum. So if the particle wants to move from x is equal to 3a by 4 to x is equal to 3a by 4, it has to traverse that distance. Okay, it has to travel from this point to this point. So when it travels from x is equal to a by 4 to 3a by 4, it has to even touch this point, x is equal to a by 2. So if the particle moves from a by 4 to 3a by 4 through x is equal to a by 2, it means at least for a fraction of a second it has to spend some time at x is equal to a by 2. So we should expect at least a minimum value of probability at x is equal to a by 2. Okay, probability cannot be 0, but what we are predicting here, at x is equal to a by 2 the probability is 0. Okay, and on both these sides you have maximum probability. The same thing happens here. Here the probability is maximum, here the probability is maximum, here is the probability is maximum, but at these 2 points the probability of finding the particle is 0. So how come the particle can move from this maximum probability point to this maximum probability point without touching this point? This is unanswerable. From classical point of view it is unanswerable, but quantum mechanical views, quantum mechanical calculations or predictions are very weird. Probably this may be due to the dual nature of particle. Okay, according to classical theory a particle behaves as an ordinary particle, but according to quantum mechanics the particle, especially a electron, is not an ordinary particle. It has both particle as well as wave nature. So probably because of the wave nature of the particle we are expecting this type of results which otherwise are not observed, okay, in quantum mechanics. So all these explanations are beyond our common sense or beyond the theories that we learnt in classical mechanics. Okay, so these are a bit difficult to digest, okay, at the beginning, but if you go through the materials and if you go through these videos, not just my recorded video, you can also go through the other videos in the YouTube. So slowly and gradually you will start understanding this concept, okay, but it requires a regular practice. So these are some of the important characteristic features of energy and wave function associated with the particle in a one-dimensional box. Okay, why I elaborated this in detail is because some of the discussions that I have commented here will be very useful for future discussion, because they are the fundamental or backbone of quantum mechanics. The results are fundamental for understanding the quantum mechanics in detail, and also some of them are very useful for you in the application of quantum mechanics, especially to spectroscopy. Okay, so this is what we have to study for the coming class. In the next class we will discuss about the application of Schrodinger wave equation to particle in a three-dimensional box. So already we have applied it to a one-dimensional box. In the next class we will discuss about what would be the energy and the wave function of a particle trapped in a three-dimensional box. So it is a simple extension of a one-dimensional problem into a three-dimensional problem. And we will also discuss a special case of that three-dimensional box, okay, from which we will develop a new concept called as degeneracy. Okay, so you have already in your inorganic chemistry course you have studied about degenerate orbitals, d orbitals. Okay, so you already know what is degeneracy or degenerate orbitals. So we will see that these degenerate orbitals arises because of the application of quantum mechanics. Okay, so with this I conclude. Thank you.